All right, so purpose of today's lab is simply to look at whether mechanical energy is conserved as perfectly as we say it is in a lot of the problems that we do. Obviously, the answer to that is no. Okay? In the real world, there are non-conservative forces like friction that are going to make it seem, or make it actually true, that our final mechanical energy is less than our initial mechanical energy, even in a conversion as simple as having a cart roll down a ramp. Okay? We're going to lose some energy. What we're going to look at is how much energy? How efficient is that conversion? Okay? Where does that energy go? Okay? Does it turn into other forms? What are those other forms looking like? That's what we got to look at today with this lab. All right, so the problem we're investigating, how much of the mechanical energy, kinetic and potential, of an object is conserved in a mechanical energy conversion. So when we're looking at this situation, we are starting with a cart at the top of a ramp. That cart will start with an initial velocity of 0. We will release the cart and it will roll down the ramp, converting potential energy into kinetic energy. Okay, so we'll be comparing the top of the ramp with the bottom of the ramp, okay, and seeing how our data looks at that point. All right, so we want to identify and explain the manipulated, responding, and controlled variables. Okay, so some things that we're going to be looking at in the lab. Okay, we want to compare the potential energy with the kinetic energy. Everybody with me there? Does this lab work if I don't put the cart at the top of the ramp? No. All right, so in other words, there's no lab unless I manipulate the initial energy of the cart. Because I'm trying to compare that to the final energy of the cart. That's subtle enough? Okay. And so I'm hoping that the final energy of the cart is somehow dependent on or responding to the first part. Now, we are going to run 3 trials. The procedure says like 5, but we're going to run 3. Okay, we're going to run 3 trials of this, okay, and we're going to average our data. What do I need to make sure are some things that should stay the same throughout the lab? That's what you need to figure out for your controlled variables. I'm not mentioning any of them. Okay? You need to figure out all 3 of your controlled variables. Remember, you're explaining them. How are they being controlled? What effect would they have if they're not being controlled? Okay? Keeping in mind that gravitational potential energy is one of the forms of energy we're using, and it's kind of dependent on something we would not directly control, but hopefully won't change. Okay. Now, for our hypothesis, here's what we're looking at. Okay? Since we're comparing the conversion of one form of energy into another, the if part of our hypothesis should talk about the law of conservation of energy. Okay? What does it say about the conversion of mechanical energy from one form to another? Okay? Something like that in the if part. Now, you can look at that from 2 standpoints. You can look at it from the ideal world standpoint or the real world standpoint. It's up to you. Okay? If you want to look at it from the real world standpoint, then you should probably say that the energies are going to be different. If you're looking at it from the ideal, then you're saying energy is always converted 100% of the time. Okay? So you have to. It doesn't matter which way you do it. Your data is going to say something. It's going to say the same thing. Okay? And then you just have to explain differently in your conclusion. Okay? One way you might end up accepting it, and one way you might end up having to explain some stuff and maybe reject it. Okay? In the end, it doesn't matter. One way is not more correct than the other. All right, the and part describes the experiment same as always. Okay, in the then part, you need to predict the relationship between the final and initial energies. Okay, that is, are they going to be equal? Are they going to be different? And some possible reasons why. Okay. Okay, so predict your results and explain. So there's not a lot of data that needs to be collected in this lab. Okay, like literally I had all of my data collected in less than 5 minutes. Okay, I set up the lab. Tyler caught the cart for me when I let it go down the ramp, and I literally had all my data in a chart 5 minutes after that. Okay, so the collection of data here is very, very easy. You're going to build a ramp setup like this. The ramp shouldn't be more than 20 centimeters high. Okay, mine was 21. Cart went a little further than I would have liked it, which is why Tyler had to catch it on the next trial, because it actually ran through the desk and smashed into one of them. But it didn't break, so that's good. I didn't have to punish myself. Okay, so 20 centimeters is a pretty good number. I wouldn't go any higher than that. The cart will go really, really fast, and then at the rate that collects data, it may actually miss some of the data we want. So I wouldn't go higher than 20. Okay, so you're just going to build a ramp like that, and you're going to record the height of the center of the cart when it sits on the top of the ramp. Okay, so your cart will be here. Okay, you will measure the distance from the floor to the center of the cart, because that's where we assume the center of its mass to be. That's the height it's starting from. Everybody follow me on that? So just take a look next to it and eyeball. Okay. So you'll need the mass of the cart and the initial height of the ramp, and you're going to do that the same way every time, so you really only need to measure it once. For the kinetic energy, we're doing 3 trials. We need the mass of the cart, which you'll already have. It's actually on the cart. Okay, so remember, each cart has a piece of masking tape on it with the mass written on it. Okay, so you don't even have to put them on a balance. The mass is on there for you already. Okay, so you put them on there. You put them on the track, and then you'll let them go. Now, we noticed the last time, and I noticed this when I was doing the lab, I needed to actually press the start button and then wait until I saw the app actually starting to do something on the graph before I released the cart. Okay? Now I did that as one person. You'll have a group, so you'll be able to do it probably better than me. Okay? But I was watching it. When I saw it starting to make lines on the graph, then I released the cart because I knew it would catch the data. We had that problem with the last lab. People were letting the mass go, and the app hadn't started recording anything yet. Okay? So make sure the app is actually recording before you release the cart, because you only actually need one thing from the app, and that's the maximum velocity for each of the 3 trials. Okay, so all you're going to do is go through the data, the velocity data, and find the biggest number. That's the one you record. Okay, everybody follow me on that? So you have a chart in your report that looks like this. Okay, so you got trial 1, trial 2, trial 3. Okay, you're just going to go through your trial data and look for the biggest maximum number. Okay, for mine, they were within 1/10 or 2/10 of a meter per second, all 3 trials. Okay, so they were really close. It's pretty consistent. You're putting the same cart on the same ramp and letting it go the same distance every time. It should really be close. Okay? Your height, obviously you're measuring that first, and it'll be the same for all of your trials. For me, it was like 21 centimeters. Right? So you'll be filling in that chart with that data. Okay? So you'll need to record the final speed of the cart, or the maximum speed of the cart. Okay? The initial height of the ramp, and you have the mass of the cart. Okay? You will also need to calculate the length of, or measure the length of your ramp. Okay, so put the meter stick on there. If you have one of the wooden ramps, if you have one of the metal ramps, they actually have a measurement on there, but it doesn't go all the way to the end, so you'll also have to measure them in the ruler. Okay, so you'll need to measure the length of the ramp for one of the analysis questions. So make sure you measure that as well. Okay, and like I say, we have the cart's mass written on the blue tape there. Okay, so we've talked about the procedure. So we're doing only 3 trials, not 4. It says do 3 more, but we're only going to do 3. Okay, and then you'll fill in that chart. Now, for your analysis, the first question just wants you to calculate the potential energy of the cart at the top of the ramp. Show me that calculation. Okay, show your work. Calculate the kinetic energy at the bottom of the ramp using your average speed. Okay, so remember, you're going to be using whatever value you have in here. Okay, your average speed for that. Okay, and then for question number 3, did the potential energy of the system equal the system's kinetic energy? Yes or no? Then why or why not? And suggest reasons for your results. Okay, question number 4 is going to involve some calculation and some thinking. Okay, friction is likely responsible for the difference in energy. Okay? Use the difference in energy to calculate the coefficient of friction between the cart and the ramp. All right, so this is actually a work energy theorem question, question number 4. All right, we know there's a difference in energy between the top and the bottom. We know that that's because work was done against the force of friction. Okay, there's a bit of calculating to do there, but I know you guys can handle it because we've done questions like that already. Okay, you need to calculate the coefficient of friction between the cart and the ramp. Remember, this really is an inclined plane. Okay, and it's an inclined plane using work energy theorem. We've done a bunch of those. And that's also what you need the length of the ramp for. All right, question number 5. What can this lab tell us about the efficiency of mechanical energy conversions? Now, how do we calculate efficiency? Anybody remember from Science 10? Okay, so Science 10, okay, tells you that efficiency is your output divided by your input. For us, that's going to be our kinetic. Whoa, that was weird. That's going to be our kinetic energy divided by our potential. Our potential is the input energy. Our kinetic is our output or final energy. Okay, if you divide those two, you'll get a decimal, like you do when you figure out your percent on the test. Okay, that'll be your percentage of efficiency. Okay, and then question number 6. Okay, so question number 5 isn't just asking you to calculate it, it's saying, what does it tell us about the efficiency of mechanical energy conversion? Are they high? Are they low? Are they good? Are they bad? Does a lot of energy get lost? Where does it go? Okay, and then number 6, what are some ways to increase the efficiency of that conversion? So suggest a few things. Okay, what in that situation, a cart going down a ramp could make the energy, or it could make the conversion more efficient? What are some ways to reduce the loss of energy between top and bottom? Right? Conclusion, same as always, copy paste your hypothesis, using your data, explain whether it was right or wrong. Okay? And then evaluation, sources of error, suggest improvements. Okay, we know we're using these tracks, we know there's some flaws with the tracks, okay, that we can name, okay, and identify and suggest improvements for. Okay. Questions on what we're doing? Right, so the collection of data really shouldn't take very long. Also, Mr. Dickey and myself, we fixed the wooden ramps. Before, we couldn't use the wooden ramps with the new carts, but we took them down to the wood shop and we carved the grooves in. So now the new carts will also work on the wooden ramps. Just don't use the big grooves. Okay, use these 2 little grooves. Okay, they're perfect for those brand new carts. Okay, make sure you have somebody at the bottom of the ramp to catch the cart when it comes off. Otherwise, it'll roll into something like it did for me. Luckily, it didn't break because it was actually moving pretty fast when it hit that desk. Okay. That was very lucky. Right. That's what happens when you do science by yourself. You should never do science by yourself. Always do science with a friend. All right. So grab what you need, which is basically just a cart and a ramp and a ruler, right? And then you guys can get started on it, okay?